This video is the first in a series of videos about the content of a textbook that I'm outlining for my own research. It's called Ideals, Varieties, and Algorithms. It's basically an introduction to algebraic geometry. And what I'm doing is I'm outlining different chapters and sections in this book that are related to varieties in projective space, because that's related to the research that I'm doing with vortex statics, really. But I thought, since I was outlining it anyway, I thought I might make a video series so that other people could learn algebraic geometry along with me. This video will be based on section 1.1 of this textbook. Chapter 1 is about geometry, algebra, and algorithms, and 1.1 is just some preliminary definitions about polynomials in affine space. So the big picture is that eventually we're going to be interested in affine varieties, and then eventually we'll talk about varieties in projective space. But for right now, affine varieties are fine. An affine variety is just a curve or a surface, and that curve or surface would be defined by polynomial equations. Then in order to talk about that, we need to talk about some algebra, and we need to talk about something called an ideal, which is related to this concept of an affine variety. And so this first video is pretty basic. We're just going to come up with some definitions and context that will eventually get us to this point where we can discuss affine varieties. In this video, we're going to discuss the following. We'll define a field, probably in the same way that fields were defined in your algebra class. We'll talk about why we're interested in fields. Then we will talk about polynomials. In n variables, which will typically be denoted by x sub 1 through x sub n, with coefficients in an arbitrary field K. As part of our discussion of polynomials, we will define monomials and the total degree of a monomial. Then we'll define polynomials. We'll have some special notation for these guys. And then we'll talk about something that's not a field, but it's a commutative ring. And we'll be interested in a specific kind of commutative ring called a polynomial ring. So we'll define those. And then we'll define some other terminology related to polynomials, such as coefficient of a particular term, a term of the polynomial, the degree of the polynomial, or I guess this will be total degree of the polynomial, whereas this is total degree of the monomial. Let's say f, where f is a polynomial. And then after we've discussed polynomials, we'll talk about affine space and what that means. Now, you are probably already familiar with affine space. It's just the fact that no one has ever called it affine space that will make this unique. And actually, maybe unique's not the right word. But we're going to define the term affine space. Then we're going to talk about the relationship between polynomials and affine space. And actually, maybe in this video, I'll just go up to affine space and we'll talk about the relationship between polynomials and affine space in the next video. So let's just start with the definition of a field. Fields are going to be important for us because we are interested in these polynomials, which are related to the affine varieties, and the coefficients of those polynomials will come from an arbitrary field that we'll denote by k. So a field is just a set and we're going to define, or we're going to notate that set by k. And it usually has two binary operations, or it will have two binary operations, multiplication and addition. And in a field, basically all of the things that you're used to being able to do with real numbers can be done. So if A, B, and C are elements of this field, then you can add in any order you want, or not in any order you want, with any grouping you want. So we could take A plus B and add them together and then add C, or we could take A and then add that to B plus C, and either way we're going to get the same answer. So this is true for all A, B, and C and K. And that is the associative property of addition. So associativity holds in a field. And we have the same associative property for multiplication. So we could write it like this. Basically, you can change the grouping if you want to, and that's totally legal. And this is for all of these, we'll just say for all A, B, C, and K. So we've got associativity, we've got commutativity. Commutativity is where the order doesn't matter. If I want to add A and B together, that's the same as adding B and A. If I multiply A times B, I'm going to get the same result as I get when I multiply B times A. So with associativity, you can change the grouping. Let's say we can change grouping, and we'll get the same result. And with commutativity, we're changing the order. We're allowed to change the order of addition or multiplication, and we'll get the same result either way. Now I know that when I was a kid, it felt very obvious to me. Of course, 2 plus 3 is the same as 3 plus 2. And of course, 2 times 3 is the same as 3 times 2. And we looked at little rows of dots and different groupings of objects. And we said, oh, that's called commutativity. And I remember thinking that was kind of obvious. And why do we even care about commutativity? If you're watching this video, you probably already know. But for those people that don't, there are some sets and operations that don't have this commutativity property. Like matrix multiplication, A times B is not the same as B times A if you're talking about two matrices. So even though as a kid, I might have thought, well, of course I can group in any order I want. Of course I can add or multiply in any order I want. That's something that we take for granted with the real numbers, and we should, but we can't always take it for granted. It really depends on that operation and the objects that we're working with. So if you've got a set K where this holds for all A, B, C, and K, then that's pretty special. So we've got associativity and commutativity. Another thing that we have is the distributive property if you have A and you're multiplying it by the quantity B plus C, you get the same result if you multiply A and B and then you multiply A and C. So you can distribute multiplication over addition. And then we've got the additive identity element. So there is some zero element within our set. So that if you take any number in the set and you add 0 to it, you get that number back. And there's also a number in the set, we normally denote that by 1, such that if we take any number and we multiply that number by 1, we get that number back. The 0 is called the additive identity because if we add a number to 0, we always get the number back. It's what makes it an identity. Is we sort of input this and the output is the same thing. And the same thing is true over here. But this time we're adding, so we call it additive identity. And then down here, since we're multiplying, we call that the multiplicative identity. Those are special too because not every set of numbers actually contains a 0 element or a multiplicative identity element like a 1. And then we've got 2 more, the additive inverse and the multiplicative inverse. So this is if you have an A in your set, well then there is another number in that set such that you can add those 2 together and you'll get 0. So this number B is called the additive inverse and it's normally denoted by negative A so that A plus negative A is 0. Basically it's saying we can undo addition with subtraction. Subtraction is a thing because every number in that entire field has something that you can add to it just to get rid of it. You can undo that addition with a form of subtraction, which would be adding the negative A, which is the same as B. Anyways, okay, so we've got that. And then similarly, if we have a number in our field and that number is not equal to 0, or excuse me, not equal to no, 0 was right, sorry, not equal to 0. Then there is another number out there. Actually, let's use C for this one. So that if we take that number A and we multiply by C, we get the multiplicative identity, 1 back. This is called the existence of a multiplicative inverse. Of course, we had to get rid of the 0 element because you can't take a number 0 and multiply it by something and get 1. It's just not possible. But for every other number in your field, if there is another number in the field so that you can multiply it by that number and get 1 back, then we say that the multiplicative inverse of every number A in the set exists. So if we have associativity and commutativity for both multiplication and addition, you can distribute multiplication over addition. If there's a 0 element and a 1 element, a multiplicative identity and multiplicative inverse, and you can undo addition with subtraction, that's the presence of an additive inverse. You can undo multiplication with division, that's the presence of a multiplicative inverse. Then we have what's called a field. And fields are really important because everything that you learned in linear algebra works when you're dealing with a field. So in your linear algebra class, you probably worked with real numbers and complex numbers, but actually it doesn't have to be a real number or a complex number. It could be any field. So that's what's insightful about this. If someone tells you this particular set of objects with these two operations forms a field, then you know that everything that has ever been said about fields applies to your object. And that's pretty cool. That's pretty powerful. So we have that, and we're going to talk about a few different fields in our studies of algebraic geometry. Here are some commonly used fields. So this Q with the double bars represents the set of rational numbers. So this is P over Q, where P and Q are integers. And integers are denoted by this Z with the double bars. So this is an infinite set. And this is a field because you can group rational numbers in any way you want when you're multiplying or you're adding, and you still get the same result. You can change the order, you still get the same result. The distributive property holds. 0 is an element of this set, 1 is an element of that set, and if you take any rational number and you add 0 to it, you get the rational number back. If you take any rational number and you multiply it by 1, you get that rational number back. And for any rational number that we have, let's say you have 1/3, there's another rational number out there, -1/3, so that you can add them together and get 0. Or for any rational number that you have that is non-zero, let's say you're talking about the rational number 5, there's another number out there in the set of rational numbers, so that you can take that 5 and you can multiply it by something and get 1. That 1/5 actually works in that case. So that's true for all of these guys. So that means our set of rational numbers is a field. And this is the one that will tend to be used in computer examples. In the book that I'm basing these notes on. And we've got another field, you know, the real numbers. That's the interval from -infinity to infinity. This is going to be a useful field when we're wanting to graph something. So we'll use this when we want to illustrate curves and surfaces. And then another important field is the field of complex numbers. If you studied calculus, you worked mostly with the real numbers. But if you study mathematics for very long, you're going to work in the complex numbers more often than you're going to work in the real numbers. This is the field where we tend to prove most of our theorems. It's because the complex numbers have some really nice properties that the real numbers don't necessarily have. Okay, so now that we've talked about all of that was just a prerequisite to talking about polynomials. Now I know you know about polynomials already, but now we're talking about in this course, when we're talking about algebraic geometry, we're talking about polynomials and n variables. And those variables are typically denoted x sub 1 through x sub n. And we want the coefficients of the polynomial to be coefficients in an arbitrary field K. Okay, so in order to get there, we're going to define a monomial. A monomial in the variables x sub 1 through x sub n is just a product of the following form. X sub 1 to some power times x sub 2 to some power times x sub 3 to some power, and so on. Eventually you're going to get x sub n raised to some power. Now each of those powers are non-negative integers or natural numbers. So alpha sub 1, alpha sub 2, all the way through alpha sub n are, well, they're natural numbers or possibly 0. So we'll just say non-negative integers. So the whole numbers, if you prefer. 0, 1, 2, 3, 4, 5, they're counting numbers. And that is the definition of a monomial. And the total degree of a monomial is just what you would expect. You just add the exponents. It's alpha sub 1 plus alpha sub 2 plus alpha sub 3 all the way through alpha sub n. Okay, now in order to simplify our notation, we're going to write this slightly differently. Rather than thinking of this as n distinct, well, not necessarily distinct, n non-negative integers, we're going to denote this n-tuple in a certain way. So let's let alpha be this ordered n-tuple of non-negative integers. In that case, rather than writing our monomial this way, just for shorthand, the notation that we'll use is x to the alpha. And so we'll say x to the alpha really means x sub 1 to the alpha 1 times x sub 2 to the alpha 2 times x sub 3 to the alpha 3 all the way through to x sub n to the alpha n. That's x to the alpha, where alpha is this n-tuple of non-negative integers. Now the total degree of the monomial is the sum of these, alpha sub 1 through alpha sub n. We're going to introduce this notation. It looks like absolute value, but it's not that. This with the absolute value bars around the alpha, that is going to denote the sum of those numbers here. So if these numbers were 1, 2, 3, 4, 5, this would be 1 plus 2 plus 3 plus 4 plus 5, and that would be the total degree of the monomial. Okay, so now that we know what a monomial is, we can talk about what a polynomial is. I know, we already know what a polynomial is. But we're just sort of introducing the notation that we'll be using when we discuss algebraic geometry. So a polynomial f, polynomial f in the variables x sub 1 through x sub n with coefficients in the field k is a finite linear combination of monomials. Okay, so the notation that we're going to use here is this. F is the sum over alpha of a sub alpha times x to the alpha, where a sub alpha is an element of that field K. And here the sum is over a finite number of n tuples. We can't have infinitely many of those because then it would not be a polynomial. Okay, now here's some notation. You have K and then you're going to use a square bracket. Looks like of x sub 1 through x sub n. This is the set of all polynomials in the variables x sub 1 through x sub n with coefficients in the field K. Now, I know that this notation is really unusual, but you know what polynomials are. And I think you can imagine what a set of polynomials would be. Now, we've already talked about the fact that the rational numbers form a field and the complex numbers form a field and the real numbers form a field. But polynomials also form a group of objects that obey many of these rules, almost all of these rules, in fact. If you add two polynomials together, you can add them in this order or this order, and you're going to get the same result. You can multiply them in this order or this order, you're going to get the same result. If you've got three polynomials, you could add these two and then add that one, or you could add these two and then add that one. Same thing with multiplication. There is a zero polynomial out there so that you can add it to any other polynomial and still get the same polynomial back. There's a polynomial, f of x equals 1, or f of x sub 1 through x sub n equals 1. So you can multiply the other polynomials by that 1 and still get that polynomial back. For any polynomial out there, I can multiply it by -1, and that's still going to be a polynomial, and I'll be able to add those together and get 0. The distributive property holds. This is equal to this if you're dealing with three polynomials, a, b, and c. The only one that doesn't work for polynomials, only one of these properties that doesn't work, is this last one. Because if I have a polynomial and I'm asking myself, okay, well, what can I multiply that polynomial by to get 1? The only thing that will work over here is 1 over that polynomial, and 1 over a polynomial is not generally a polynomial. So this set of polynomials in variables x sub 1 through x sub n with coefficients in K satisfies all of the properties of a field except for the last one. It doesn't have a multiplicative inverse because 1 over a polynomial is a rational function. It's not another polynomial. And remember what this says. It says there exists a C in K. So this is saying there exists a polynomial in our set of polynomials such that our polynomial times 1 over that polynomial equals 1. And that doesn't work most of the time. 1 over a polynomial is generally not a polynomial. The only time that 1 over a polynomial is a polynomial is when we're dealing with a specific polynomial, the polynomial 1. So yeah, this last one doesn't hold. And it's not because that there's nothing out there that can give you a 1. It's because that there is no polynomial out there that belongs to the set of polynomials. Like, this is the set we're talking about. So yeah, this is not quite a field, but since every other property holds for the field, this is called a ring. And it's a ring where multiplication is commutative, so we call it a commutative ring. Let me define that for you. this is a set R that has two binary operations, multiplication and addition defined on R. And I'm going to say that it satisfies the conditions 1 through 5 for fields, but not that sixth property. Commutative rings are just like fields, except they may not have the property that every element has a multiplicative inverse. Obviously, if something is a field, it's a commutative ring. So you're good there. The set of integers is a commutative ring. Let's think about that. Remember what your set of integers looks like? I can group integers. If I've got 3 integers and I want to add them together, I can group them in any way I want. I'm still going to get the same result. That's associativity. Same thing is true with multiplication. I can group them in any way I want, and I'm still going to get the same result when I multiply them. That's associativity for multiplication. We can add and multiply integers in any order we want. This distributive property holds. Every integer, I can add 0 to it, and I still get the same integer back. Every integer, I can multiply it by 1, and I still get the integer back. There's a 0 and a 1 in the set of integers that satisfies those properties. And for any integer, give me, integer of 10. There's another integer out there, -10, so that I can add them together and I get 0. But last property doesn't hold. If I'm saying to myself 10 times what will give me 1, and I need that something that I'm multiplying by to be an integer, I'm going to be out of luck, because 10 times 1/10 equals 1, and 1/10 is not an integer, it's a rational number. So the set of integers satisfies these 5 or these 6 properties. I said 6, 5 properties, and not the 6th. Basically, we can't divide them and still get an integer. If we can't divide them and still get an integer, there is no multiplicative inverse, and therefore we're dealing with a commutative ring rather than a field. Okay, let's see what else. And then this guy is a commutative ring as well, because you can add polynomials in any way, in any grouping you want. You can multiply. You can group polynomials in any way that you want. When you add or you multiply, you're going to get the same result. You can change the order. You're going to get the same result. The distribution holds. This holds, and this holds, and this holds. But if I have a general polynomial, there is not guaranteed to be 1 over that polynomial in the set of polynomials to get us a 1 back. Generally, if I have a polynomial, just x, in order to get a 1 back, I'd have to multiply by 1 over x, and 1 over x isn't a polynomial. It's a rational function. So this is a commutative ring. And it's a special commutative ring because it's a commutative ring made of polynomials. It comes up so often that we call it a polynomial ring. We like to have that name for it. Okay, so we know about the set of all polynomials in x sub 1 through x sub n with coefficients in some field k. Now you might be thinking, like, what do you mean by all this, x sub 1 through x sub n? I want to make it a little bit more concrete for you. You're already familiar with polynomials in x. So polynomials in the variable x. So y equals x squared minus 3x plus 2. You know that this is a polynomial in x. You know that x to the 5th minus 0.125 x squared plus 17. And of course, I'm just looking at the right-hand side of this. This is a polynomial in x. This is a polynomial in x. Now, if we're talking about the set of all polynomials in x, so you have to imagine all the possible powers of x multiplied by all the possible numbers k in some field. That set of polynomials in x with coefficients in k is denoted by k of x like this. So this is not just one of them or two of them, this is all of them. So you have to kind of imagine it in the abstract. Now this one had coefficients of 1, -3, and 2. So I could think of that as a polynomial with the coefficients in, oops, I don't want to use integers here because integers form a commutative ring, not a field. Those are integers, but those are special cases of rational numbers. All integers are rational numbers. So we could think of this polynomial as being belonging to this set of polynomials of a single variable x whose coefficients are rational numbers. This one with this decimal here, well, that's a rational number. Coefficients are 1, this coefficient, and this coefficient. And of course, there are some other coefficients that are there. The coefficient of x to the 4th is 0. Coefficient of x cubed is 0. That would also belong to this set of polynomials with coefficients in the rational numbers. Or we could think of these as coefficients in the real numbers. 1, -3, and 2 are real numbers. These numbers are real numbers. Or we could think of those as coefficients in the complex numbers. These two polynomial functions belong to all three of these. And all three of these are different sets of polynomials. These are just polynomials whose coefficients are rational. These are the polynomials whose coefficients are real, and these are the polynomials whose coefficients are complex. In general, we're going to say these are the polynomials in a single variable x with the coefficients in some field k, and that field k could be any one of these. So that's for polynomials in one variable. Now you've probably already seen in other classes polynomials in two variables. Now, normally we don't call them x sub 1 and x sub 2, although that's the notation we're using here. When we only have two variables, we normally call those variables x and y. So you might have a polynomial like this, x squared plus 3xy minus y squared. That's a polynomial in two variables. Or you might have another polynomial in two variables, 5 x squared minus 4 xy plus y to the 5th. Also a polynomial in two variables. The set of all polynomials in two variables with coefficients in k is denoted this way. You could denote it this way with x sub 1 and x sub 2 being the variables, but normally when we're talking about two variables, we won't do this. We'll do this instead. So this is the set of all polynomials in the variables x and y with coefficients in the field K, and K could be any field. So field of rational numbers, field of real numbers, field of complex numbers, for example. And of course, for polynomials in 3 variables, rather than calling those 3 variables x sub 1, x sub 2, and x sub 3, we typically call those 3 variables x, y, and z. So the set of all polynomials in 3 variables x, y, and z with coefficients in k looks like this. So here's your polynomials in 1 variable. Here's your polynomials in 2 variables. Here's your polynomials in 3 variables. And if we go beyond 3, usually that's when we start using subscripts. And just start calling those x sub 1 through x sub 4. They're all just polynomials, which consist of these monomials, and then you've got these coefficients from the field K multiplying the monomials, and then you add them together. There's a finite number of monomials, and when you add them together, you get a polynomial. Now here's an example. Say f is 2x cubed y squared z plus 3 over 2 times y cubed times z cubed minus 3xyz plus y squared. This is directly from that textbook that I mentioned. This is a polynomial in 3 variables. The coefficients are 2, 3 over 2, negative 3, and 1. So those are all rational numbers. So we can think of f as belonging to the set of polynomials in 3 variables, x, y, and z with coefficients in the rational numbers. Okay. So we'll come back to that one in a minute, that example. Excuse me, this is 1 variable, 2 variables, 3 variables, 4 variables, and then in general, with n variables. The n could be 15, there could be 15 variables, or there could be 2 variables, any finite number, well, any natural number of variables would work there. Okay. Now I've got more definitions. So let's say f is this polynomial in the set of polynomials in n variables, x sub 1 through x sub n, with coefficients in the field k. Here's some definitions. We're going to call a sub alpha the coefficient of x to the alpha. So over here, 2 is the coefficient of x to the alpha, where x to the alpha is x cubed times y squared times z. Okay, just as an example. Now, if a sub alpha is not equal to 0, so that means you actually have a term that looks like this in your equation. Your equation defining that function, then we're going to call a sub alpha times x sub alpha a term of the polynomial f. So for this example here, we've got 1, 2, 3, 4 terms. Two x cubed y squared z, 3 halves y cubed z cubed, negative 3 times xyz, and positive y squared are the 4 terms of our polynomial f in this example here. And then the total degree of f is the, well, it's denoted this way. Is the maximum degree of any term in the monomial, or it's the maximum degree of any monomial in the polynomial. And of course, we want that term to actually exist there. So we've got these 4 terms, and the degrees of these terms can be found this way. You just add the exponents. This is degree 3 plus 2 plus 1, so that's degree 6. This is degree 3 plus 3, which is 6. This is degree 1 plus 1 plus 1, so it's 3. This is degree 2. The maximum of these is 6. We actually have 2 terms of degree 6, the first one and the second one. So that is the degree of the polynomial. This is the degree of the term on this list, but the degree of the polynomial is the maximum of the degree of the terms. So we might write it this way, might say that the degree of f is equal to the maximum over alpha of this expression, which represents the degree of a term. So for our example, the degree of f is 6. It's the maximum of 6, 3, and 2, which is 6. Okay, so I'm going to define affine space for you, and then in the next video, we're going to talk about the relationship between polynomials and affine space. If we are given a field K and a positive integer n, we define n-dimensional affine space in the following way. And it's just a set. We write k to the n, and it's just a set of n tuples where each of those elements are elements of k. And you've already worked with n-dimensional affine space. The real line is an example of this. And we can think of that as just a k, because that's a field, and here n is obviously equal to 1. So that's the real line. And that's just a set of all real numbers, which we typically denote this way. R2, that's a set of all points, normally denoted by x and y, such that x is a real number and y is a real number. We visualize that with the entire XY plane. That's the plane, the real plane. And then R3. If you've taken Calculus 3. Here you've got ordered triples, X, Y, and Z, such that X, Y, and Z are all real numbers. And you can think of R3 as encompassing all of three-dimensional space. So these are different types of affine space. This is one-dimensional affine space and two-dimensional affine space and three-dimensional affine space, where the field in this case is the field of real numbers. Now, we wouldn't necessarily have to have one of these. You could have something like this. Maybe you've got N2. So that's a set of natural numbers crossed with a set of natural numbers. And remember, your natural numbers are your counting numbers, not including 0. So this is going to consist of, if I were to draw it in what would typically be the XY plane, the real plane, that would consist of all of these points. When x equals 1, y equals 1, and when x equals 2, x equals 1, y equals 2, and when x equals 1, y equals 3, and these points would go on forever. And we would have an entire grid of them. 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 1, 2, 2, 2, or no, yeah, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, you know, and so on. So that's what that would look like, except, oh, I don't think that that's going to work because the natural numbers, are the natural numbers a field? I don't think that they are because they don't have a multiplicative identity. They also don't have an additive, or not a multiplicative identity. They have a multiplicative identity, sure, they don't have a multiplicative inverse is what I meant to say. But that's the idea behind this notation. But this is not affine space because n is not a field. But the reals are a field. The complex numbers form a field. The rational numbers form a field. So we can come up with n-dimensional affine space for any one of those. And basically it's just n tuples where the elements of those n tuples come from that field. So this would work if n was a field, but n is not a field. Let's actually look back at those notes. Natural numbers, that works, that works, that works, that works. There's no 0. There's no additive identity. There is a 1, and it doesn't have an additive inverse. Yeah, I have 3 here. -3 would give me 0, but -3 is not a natural number, so that's not going to work. And we don't have a multiplicative inverse. If I have a 3 here, it'd have to multiply by 1/3, but 1/3 is not a natural number, so that's not going to work. So the natural numbers satisfy all of these, except for this one. We don't have the additive identity, and we don't have the additive inverse or the multiplicative inverse. So that's not a field. But if we were dealing with a field, that would be the principle. You're just going to take one element from this set and another element from this set, and then you're going to graph them as ordered pairs or think of them as ordered pairs, just like we do with these numbers x, y, where x and y are real numbers. Okay, so I will see you in the next video. If you want to learn more algebraic geometry, we will talk about the relationship between polynomials and affine space.